Complex numbers. So I want to remind you of a few things. First off, if we have the square root of -1, that is defined to be the imaginary number I, and we know that I squared is equal to -1. So let's clean up this product of two complex numbers. We have 3 plus the square root of -100 and 4 minus the square root of -9. Directions say simplify and write in A plus BI form. So we're going to use this property right here. The square root of -1 is equal to I. So the square root of -100 is the same thing as -1 times 100, all under that root. So you have the square root of -1 and the square root of 100, which is I, times 10, you get 10I. We're going to do it quickly, but that is the process. So we have 3 plus 10I. And let's clean up the second one. We get 4 minus, well, the square root of 9 is 3. And we have a negative under there, so 4 minus 3I. Now pretend this is just a variable. Instead of an I being an imaginary number, if this was an X, we would just FOIL this. So the process will be exactly the same. So first is 3 times 4 is 12. Outer, 3 times -3I, it's -9I. Inner, 10I times 4, so plus 40I. And then last, 10I times -3I, that's -30I squared. And we know I squared equals -1. I know this is already written on the side, but I encourage you to write this every time you use it. By the time you've done all your homework, you'll know it backwards and forwards. So then we clean up. So we get 12. Well, these guys both have an I, so we're going to subtract the coefficients. So we're going to get -9 plus 40, or 40 minus 9. So we get plus 31 I. Okay, and then this back here, we know I squared equals -1. Here's I squared. So it's the same thing as -30 times a -1, if we use that property. So keep on cleaning it up. So we get 12 plus 31I plus 30, and we're going to combine the constants. So we have 12 and 30 that do not have a variable with them, so we're going to add those. So we're going to get 42 plus 31I. And notice this is in A plus BI form. So we've done it. Let's continue. Let's do another one. Okay, now this is very similar. We're going to do the same steps. We are going to rewrite this in terms of i's instead of -1s under roots. So we're going to have 2 minus 5i, because the square root of 25 is 5. And then we have a square root of a -1 is I. And then we'll have 2 plus 5i. So let's FOIL it as we did before. First is 2 times 2 is 4. Outer, 2 times 5i plus 10i. Then we have the inner, -5i times 2 is -10i. And last, -5i times 5i, we get a -25i squared. Oh, look, the middle terms cancel. Okay, so we have 4. Now remember over here that we know what I squared is, right? I squared equals -1. So instead of this I squared, I'm going to write -1 minus 25 times the -1. So that ends up being 4 plus 25, which is 29. It was interesting. We ended up with just a number there. I want you to look carefully at something. If you notice, the beginning of the first term in this set of parentheses was a 2. There's a 2 also there. Okay? I should color these as well. And let's look at the bottom one instead. And if you look at the back of the set of parentheses, we have a 5i. Ignore the sign, just look at the value for now. And we have a 5i. And then look, the signs in the middle are different. Okay? We've seen this before. You may not remember, but we definitely have. So if we have A minus B times A plus B, that's very similar to what we have here. Fronts are the same. The backs are the same, but the sign in the middle is different. When you FOIL this, you've got a squared minus ab plus ab. I may have done this in reverse order. I think I did. So a squared, outer, first, and then outer is plus ab, and then inner minus ab plus, minus b squared. And then if you look, the middle terms canceled, and you were left with a squared minus b squared. Well, that's exactly what we have here. Turns out if you have complex numbers, you have like an a minus bi times an a plus bi. All you have to do is follow that form. This results in a difference of two squares if it were real numbers, right? So our numbers aren't real, but we're still going to have the same process. So all we have to do is square the front, because that's what happened here, right? So the front term are both a's, so a squared. And then we put a minus sign, and we square the back. Well, bi is the back term, so bi squared. So we get a squared minus b squared I squared. That again, I squared is negative 1. So we get a squared times negative b squared times a negative 1. We get a squared plus b squared. This is going to be really useful. The reason this is important, that we care so much about this, is over here you notice both of these had i's in them. When we multiplied by the same term in the front, same term in the back, changing the sign, we call that the conjugate, we ended up with a term with no i's in it. Look over here when we did it in general. A minus bi, a plus bi. Both of them had imaginary parts. When you do this process, the i's are gone. You end up with some real number squared plus some other real number squared. So these are really interesting, really helpful. We call these complex conjugates. Okay, so a plus bi and a minus bi are complex conjugates of each other. You've probably heard conjugate before we talked about complex numbers. Term in the front is the same, term in the back is the same. We've changed the sign in the middle. We're going to use this to clean up more complex numbers. Okay, so simplify and write an a plus bi form. The very first thing we're going to do is we're going to rewrite this. Instead of with negatives under our roots, we're going to rewrite this with i's. So 3 plus 9i, and that's divided by 5 plus 2i. Okay? We don't want the I on the bottom. Even though it doesn't look like anything, scary here, the I, remember, is a square root. And often you've heard that you want to rationalize a fraction that has a root on the bottom. So that's still going to be our strategy, but we have to go about it a little bit differently because we have the sum here. When you were doing some of your earlier classes in algebra, you might have had 5 plus the square root of some number, and you multiplied by the conjugate. Now we're going to multiply by the complex conjugate. So let's make a note. So complex conjugate. We are going to multiply by the complex conjugate of the denominator. Okay, so my denominator is 5 plus 2i. Okay, the conjugate of that means we keep the front the same, we keep the back the same, and we change the sign in the middle. So we're going to multiply through by 5 minus 2i over 5 minus 2i. Remember that this right here is an expression. The only thing mathematically we are allowed to do to an expression is multiply by 1 or add 0. So if I multiply by the number 1, I have not changed the expression. That's what the rules of algebra tell us. Well, we're going to multiply by a special number 1, and you've done this before. But we're going to multiply by the complex conjugate over itself. This really is the number 1 because you're multiplying by something over itself. Okay. Now we're going to handle this the same way we did with the other two examples. We are going to FOIL. Remember, when you have a fraction times a fraction, You multiply the numerators. And you also multiply the denominators. And just rewrite the fraction. Okay? So we're going to do that. So we're going to FOIL the top. So 3 times 5, that's the first term. So 15. And then we do outer 3 times negative 2i, that's negative 6i. Inner is 9i times 5, so plus 45i. And then last, 9i times negative 2i, we get 9 times 2, 18, but it was negative, negative 18i squared. Take just a moment and make sure you can reproduce that. First, outer, inner, last. I'll label them. First, outer, inner, last. We're going to do the same thing with the denominator. Oh, but do we have to? Do we have to do all that work? We certainly can, but we chose this denominator over here on purpose because we wanted it to be the complex conjugate. So all we have to do here is rewrite the first term, squared. Then put a minus sign, then rewrite the back term, squared. Okay? Or you could FOIL it. FOILing works too. So 5 squared minus 2i squared. Because this is that difference of two squares. Remember, if we have a minus b times a plus b, that's a squared minus b squared. That's all we're doing. Let me clean up the numerator. 15, well, we have two terms with i's in them, so we are going to combine their coefficients. We have negative 6 and we have a positive 45, so we really have like 45 minus 6. So that's a plus 39i. Okay? And we also have an I squared. We know I squared is equal to negative 1. So this is going to be replaced with the negative 1. So we're going to get negative 18 times the negative 1. Same thing on the bottom. We're going to have a 25. We're going to have a negative 4i squared because if you have a times b to the n power, that's the same as a to the n times b to the n. So that's what we're doing here, right? 2 squared, I squared. So here we go. But we also know that I squared is negative 1. So we have this and this are both going to get a negative 1 instead. Okay, let's keep on cleaning it up. So 15 plus 39i plus 18 over 25 plus 4, because that negative 1 right here, I'm sorry, that I squared rather is a negative 1. Okay, then we keep cleaning it up. 15 plus 18, 33 plus 39i over 29. But the directions said write an a plus bi form. Well, this is one big fraction. I need to clear cut a plus sign or a minus sign, and I need a b, and I need an I. So I'm going to have to tweak this a little bit. So remember your rules of fractions. So a over c plus b over c. You can rewrite this. Rewrite the common denominator and do a plus b. Well, this is an equal sign, so I can go this way or I can go this way. So I can rewrite this as 33 over 20. 39 over 29 times I. And we see that this is a plus bi form.